Yeah. All right, so I wanted to start, I'm going to go through star formation today with a sort of, again, a perspective of trying to follow where the molecules of life, what's the path that they take. But there'll be a lot of physics in this that I can't run away from, so I'm going to subject you to some of that, but I think that's good. I do start with a couple of pictures, well, one picture and one spectra, and just to show you, the universe is amazing, right? So this is one star from a region. It's in the Perseus constellation, and it's called NGC 1333. And all of these things, so there's a cluster of stars being born here. Every star you look at here is probably 300,000 years old, give or take, maybe 100,000. And what you see here, these are the outflows. So when the star is born, it's accreting matter from the disk, conserving angular momentum, and it ejects material along the poles because it can't eject it in every direction because the disk is there. So you see an outflow here, there's an outflow here, this is all outflow material, there's a big outflow here, and the whole place is just filled with stuff. So it's really a fascinating and beautiful picture that was obtained from by the Spitzer Space Telescope, and it can be attributed to Rob Gudermuth. Now, also, the other thing that happens in star-forming regions is many of them exhibit a very rich, complex chemistry that is dominated by the formation of simple organics. These are complex organics by interstellar standards, right? Because if you think that we're starting with atoms, and when you get to 5 atoms together in a molecule, that's actually complex for space. But they get even bigger than that. And these molecules emit. They emit emission lines or perhaps absorption lines. So all of the stuff you see here are different molecules emitting, telling us that they're there. And I'll go through a little bit of that. And finally, one of the things we talked about very briefly when people asked me questions was the so-called Nice model, and I described what that was. And I thought I would show it because this is just fun. So again, this is a model of the solar system after the gas. So you have a gas and dust disk, you form the planets, and you have the leftover planetesimals. So this is Jupiter, Saturn, Neptune, Uranus, and this is the proto-Kuiper belt sitting here. And this can be attributed to Alessandro Morbidelli. And then I'm going to let this run, and you're going to see there will be interactions between Jupiter and Saturn that eventually will lead to complete chaos. So time up top there, that's about 200 million years. That goes crazy around 900 million years. So you can see that there's some interaction. So these are Kuiper belt objects being ejected, the stuff that you see going out here. So they're interacting with some of the planets. So focus in on Saturn here, and you're going to start to see it get excited that it has gravitational interactions with Jupiter. Somewhere near, I think it's the 2-to-1 mean motion resonance. And here we go. It's getting more, and then this interaction then throws Neptune in the proto-Kuiper belt. The interactions with Neptune then basically evacuate that area and potentially send material into the inner solar system. Of course, you're also sending it away. And that's just something I thought we should see. Okay, so we're going to try and follow stuff. So I'm going to start today with the initial conditions, the birth of the star. Whether I get to protoplanetary disks, I don't know. I'll try to. I'll talk probably tomorrow about some aspects of the planetary composition, the meteoritic record, and the chemical composition, cometary composition. And then I'll talk about what fractionation is and why that is useful. And again, I'm going to try and follow the CHO and the N, but also try to find and observationally characterize the seeds of the Earth. But before that we do that, we have to know how we do that. And David mentioned the dipole moment. That's a very crucial thing for astronomy. So you have a molecule sitting there in space, and it only interacts with radiation if it has a dipole moment. And it's due to the distribution of positive and negative charges. So water is a good example because the positive charges cluster on this end and the negative charges cluster near the oxygen atom. So when this thing is spinning, it actually acts like a little antenna that can receive and emit electromagnetic radiation that actually coincide with the specific frequency that that molecule emits. Now, when you want to talk about, we're getting into molecular physics, I love this picture. This is molecular force microscopy. So what you're looking at is a molecule, and this is the force field that's binding the molecule together. When I saw that picture, I was like, wow, that's cool. That's physics in action. Okay, so we look at a molecule. A molecule has, the protons, right, the different atoms, the protons in the different atoms, but it also has the electrons. Now, when we normally think of spectroscopy, there's an atom, an electron. An electron can go to an excited state, right? And it can decay downward, and when it does, it emits radiation at a specific wavelength. So Lyman alpha, that's basically the fundamental transition of the hydrogen atom at around 1200 angstroms. This is one example. So molecules also have electronic states, but they also have the nucleus that can rotate and vibrate. So there's other motions that can actually lead to energy. All right. So the way this works is that the electrons are lighter than the nuclei, so they have a much faster motion, more cycles of electrons moving around, while from their perspective, the nucleus, the protons and neutrons are just standing still, okay? And so what we do is you assume that you can treat the electronic motion as sort of separate from the nuclear motion. And what the electron does, of course, depends upon the distribution of charges in the nucleus. So if the molecule is, say, vibrating and the distribution of charges is broader, then that's going to affect what the electrons can do as well. So it's a complicated business. But you can boil down the complications to some really simple physics that describe what's going on. So, molecules are a mess. But if you look at their Schrodinger equation, they can have both complex, you have different Schrodinger equations can be broken up for the nucleus and the electrons, okay? But everything is confined to a certain diameter, all right? So you can then just take, here's the average momentum of a given particle, h over 2 pi r, all right? You have the uncertainty principle, that's the momentum, the uncertainty in the momentum, certainty in the position is greater than h over 2 pi. We know that if you've taken a basic physics class, all right? Now, the kinetic energy spacing, you can express the kinetic energy in terms of the momentum. That's right here. So that comes into this. So now, if I can look, I just put in the mass here. It's the only parameter that matters in this case. Mass of the electron is much less than that of the proton, right? So the energies of the electronic motions are on the order of about 10 to the 4th Kelvin, whereas the energy of the nuclei are on the order of about 10 Kelvin. That's a big difference, right? And so that tells you that these things are going to be tracing different regimes. That is, if you have a molecule, the electronic motions are only going to be probing areas where there's exposure to hot gas or radiation, that's that temperature. And the nuclear motions are going to be probing much, much colder regimes. Okay? So, what does that mean? We have different molecular transitions. So there's the electronic transitions. Their typical energies are a few electron volts, so that's hot. But interstellar space is filled with lots of hot things. There's vibrational transitions. So a molecule can do this, it can do this, it can do the funky chicken. It can do all kinds of vibrations. It also can do the little spin motions. So these are typical energies of on the order of about 1/10 of electron volt. And then it can rotate, which have sort of milli eV. regimes. Okay, so that's the basics on how things emit. Now what we want to do is we want to determine quantities. You know, if you want to think about star formation or understanding the physics of something, and in astronomy, the fundamental unit that we always try and get at is the mass, right? You know, if you want to think about, we know that gravity plays a role here. That's what starts the collapse and dominates the collapse. And what's the main parameter for that? Well, it's the mass, and of course the mass is balanced with thermal pressure. So we want to get the mass, and we want to get at the temperature. So we'll talk about mass first, and I'll get the temperature in a little bit. Then you run into a little problem with getting mass. And that is, you know, the most abundant molecule in the universe will be H2, will be molecular hydrogen. That's the most abundant element, right? And so that is the mass. So what you want to do, okay, is I want to go out and I want to observe H2 in the regions where stars are being born. So stars are born in molecular clouds dominated by H2. I want to observe that, okay? But as was noted earlier, this is a homonuclear molecule. So thank you, David. It has no charge different, no permanent electric dipole. Now, unlike in atmospheres, the pressures of interstellar space are lower than the best laboratories on the Earth. There is no induced dipole in this instance. Instead, what H2 does have, it has a quadrupole. And what that does is actually makes the spacing be a little bit bigger. So its first transition has a delta E of 510 Kelvin. Okay, that's whatever that is. Now we can describe the populations. So what we have here is a molecule, right, with different states. So we'll say this is the ground state, right, and this is the first excited state. So you have some molecules are sitting up here in this state, they're spinning, right? And then they slow down and they emit a photon and that comes off and we observe it, right? So what you want to know is, well, what is the fraction of population, or the fraction of molecules that are sitting in this excited state? That's what basically is giving you the emission. And if you can know what that is, then when I observe this emission, my integrated emission, so it's integrated of, say, some intensity over wavelength, right? That is essentially going to be proportional to the column density of molecules along that line of sight in the upper state. So what do I mean by that? Column density. That's another fun quantity. Now we talked about that a little bit earlier. So you have your cloud here. Again, our telescope, what you're observing is basically a column through the cloud where you count all the molecules in that object per cubic centimeter. Again, astronomy works in CGS units. So, okay, so it's proportional to the upper state. So if I can figure out how many molecules are in the upper state, I can convert that to a total column density per centimeter squared, okay? And then if I know the distance to my object, I can figure out, you know, what this is here, okay? That's some delta length or delta R or whatever it is, right? I can then convert this column density to something that's more conclusive of the total mass contained in that volume, all right? So, the way we do this is we use the Boltzmann equation. So you have the upper state over the lower state is proportional to the statistical weights, and this is delta E. All right, so statistical weights are some property of the physics of the molecule, and you can look them up. It's not that hard. So upper state, the population, that's the density of molecules in the upper state over the density of molecules in the lower state. So if we take this and apply it to H2, here's the lowest state. It's 5/3, that's the statistical weights, e to the minus 510 over T. The typical temperature of these objects is 10 K. So that's e to the minus 51. That means there are no molecules sitting in this state. All H2 molecules are sitting in the ground state in molecular regions. So that's a pain in the butt, right? That's just, you know, physics of the universe throwing you, a little bit of a problem. All right? So, how do we get at this very fundamental problem? We have to use proxies. So, in this case, what we have now instead is we use other things where we have calibrated them. So we have carbon monoxide. The delta E of its first transition is something on the order, well, it's a twiddle here. It's on the order of 5K. All right. So now instead of e to the minus 51, I have an e to the minus something like a half or something like that. That's much less. So what I'm doing is I'm putting e to the minus 5. The temperature's 10 here, and these numbers are not that much different. So there's significant population for CO to emit for us to observe and see it. Okay, so that's physics, and then all I need to know is how much CO is there compared to H2. What's its abundance? So that gets into chemistry. All right, so that's a fun little astrophysical problem, but that's why we go out and we observe carbon monoxide everywhere. It's one of the most abundant, stable molecules around, and here is the map of our wonderful galaxy emitting in the first transition, first rotational transition of carbon monoxide. So this is basically where all the stars are being born in the galaxy today. Okay, so another thing that we have to pay attention to are isotopes, right? So these are slightly different weights, if you will. So 12 carbon, 13 carbon, 14 nitrogen, 15 nitrogen. They have a slightly different weight, slightly different motions. So their positions where their lines show up in the spectra will change. And these molecules, the abundances of the isotopes are different. So 12 carbon is 90 times more abundant than 13 carbon, as I said yesterday. So that's very advantageous, actually, because David talked about optical depth. The lines of 12CO are generally optically thick. What does that mean, right? Again, that means that we're only seeing the surface of this object if the line is optically thick. We're not seeing through it. So astronomically, I can then go and observe a molecule that's identical, 13CO. It's the same molecule. Just has a lower abundance because it's another isotope. So it has an optical depth that is 90 times lower than that of 12CO. And then all of a sudden, I can see the entire line of sight and map out the mass in that object. So it's a very powerful tool, and it's something that we do again and again and again. All right? And these isotope ratios, they're one thing what they are in the sun. That's not necessarily what they are in the center of the galaxy or at other positions in the galaxy. They vary with position because it depends upon where the isotopes are being produced. There's higher star formation rates in the center of the galaxy, so they're making more of these various isotopes. Okay, so we have the various regimes and how we probe the spectroscopy. We have the optical and the ultraviolet radiation, so that's telescopes, ground-based telescopes, the Hubble Space Telescope. They can observe excited electronic space. The near and mid-IR give you the vibrational modes of solids and also gases. So this would be ground-based telescopes. The Spitzer Space Telescope was in this regime. The mid and far IR give you the rotational lines of various molecules. And the far IR would be Herschel or Sophia. The submillimeter and millimeter, low energy rotational lines of many molecules. This is ALMA. It's the big thing right now. I'll show you as much ALMA as I can, which is not much because there's a lot of data, but it's sitting on people's hard drives. And it's difficult to analyze. And then there's the centimeter wave, the VLA, where you have things like OH and ammonia and formaldehyde and various other molecules that will emit. Okay, so now what does this mean for understanding star birth and following things. So here is sort of this temperature density diagram that I came up with. So you start out in the diffuse medium, so things, the general ISM actually is up here at 1,000 K, 1 particle per cubic centimeter. And then you get slightly denser, but still atomic and turning into molecular. And that's where you're in the sort of 50 to 100 K and a density of about 1,000. And then gravity begins to win and you start to condense. So you make your molecular cloud, that would be right here. And these would be the dense cores, where you're colder now. You're blocking out more stellar radiation. So you could talk about heating and cooling in the interstellar medium. The heat is coming in from the outside. It's starlight. All right. What's absorbing the starlight? It's the solids. I'll show you that. It's the interstellar grains. And they absorb the energy of the optical starlight, the UV starlight. They re-emit it in the infrared, and they also transfer that energy via collisions to the gas. Okay, so that's why you're down here at 10K. There's other mechanisms that can heat the gas as well. Then the star is born. You have to get denser. You also get hotter as the star puts energy into the system. And in the disk itself, there are low-density cold regions, low-density hot regions, high-density cold, high-density hot. It's everywhere. And so that's really opens up the regime. So what are we talking about? Well, these sort of regimes are where you get the lower rotational lines. Now, what is that? What do I mean by that? So you have, the delta E of the lowest rotational transitions, what I talked about, right? There's many rotational transitions. There's higher energy ones and lower energy ones. And J is just the angular momentum. So it's saying how quickly is it rotating. That's all it is. All right? And then you can have the vibration of organics. Here we have the vibration and rotation lines of sort of lighter molecules and the higher J ones, and then the electronic transitions would be up here. And of course there's ways to probe all these various places. Now, one last little thing before I launch off and try and talk about star formation. So you can also define something called the critical density. That is the density at which a molecule or a transition of a given molecule will likely probe. And that is equal to the spontaneous emission coefficient, so the Einstein A coefficient, which is proportional to the dipole moment, the frequency, and then something to do with the transition itself. So it goes as the dipole moment squared. All right, and then this is a collision rate. So this is per second, and this is centimeter cubed per second. Right, so this comes out to be per centimeter cubed. All right, so when I stick these things in, there's a dipole moment squared. What that means is things that have a low dipole, such as CO here, this traces low density gas. And heavier molecules that have a bigger charge disparity, so CO doesn't have much charge disparity, because it goes that they actually probe higher density gas. So we can actually see this, and I'll show it to you. So different molecules probe different regimes. And chemistry also plays a role in that as well, but there's some basics of molecular astrophysics that lead to higher dipole moment molecules tracing higher density gas. Okay. All right, that's the gas. There's also the dust that we have to pay attention to. There's the dust absorption, and then I'll talk about dust emission later. So here you have a star. So this is a great article if you want to understand something about extinction by Fitzpatrick. So you have a star here and another star that's very similar. Here's the spectrum of the star. Okay, here, when you point your telescope here, you observe this spectrum. So that's flux versus wavelength. Now, if you have a cloud of dust in between you and it, or some sort of solid particles, you get a preferential absorption of the shorter wavelength starlight. Okay, so here you see in this representation, this part of the spectrum is not much affected, whereas this is very heavily affected. All right, and so this has been known for a long time, right? So we know that there's dust absorbing starlight out there, so people have models of it, and There's lots of really great ones out there. So Weingartner and Grain is one example. Another one would be Ostenkopf and Henning, and there's others. And so what this is the extinction curve. So this is the effect of extinction versus 1 over wavelength. So it's magnifying the part where extinction is the highest on the short wavelength side. Okay. So there's more extinction by grains, and there are models again that show this is both due to silicate material and also carbonaceous material. So a combination of both silicate and carbonaceous solid particles. Now, this is perhaps another representation of that. I love this picture here. It's very serene with this beautiful star field. This is one object. It's called Barnard 68. It's a black hole in space, just this dark object. This is when you look at it in the visible at 0.4 microns. Now, when I go to longer wavelengths, all right, so going this way and then down here, so this is 2 microns, 1.2 microns. So as I go to longer and longer wavelengths, the effects of absorption of starlight start to go away. All right, and why is that? Well, this object, this particular molecular object, is superposed on the galactic bulge. This is incredibly rich star field here. And when you get to these longer wavelengths, all of a sudden, I can see through this thing and see all the stars that are hidden when I just look with visible light. Okay, that actually tells us something about the size of the particles. It tells us that the typical size of the particles is on the order of about 1/10 of a micron. So just to give you an idea, this is human hair, not obviously to scale, and this is a micron. So the typical size of the particles in interstellar space are, 0.1 of that, so teeny, teeny, tiny particles. Now these particles absorb that starlight. So here's another one. This is called the elephant trunk, right? And then they re-emit that energy, right? Energy is conserved. So here is the absorption in the visible. It gets re-emitted as heat in the infrared. All right, so this is an optical picture, and this is a picture from the Spitzer Space Telescope. And so you see all this diffuse stuff emitting here is the stuff that's basically dark here. There's other things going on, right? You see all these stars here that you don't see here? All right, some of those may be background objects, but actually other ones are young stars that are being born out of this material. And there's ways of figuring out which is which I'll talk about as we go. Now I'd like to just do this. It's a nice picture, right? So let's pick one of Van Hulst's stars here, just as an example here. So here we have this star field, and that star is emitting light. Now if I put a cloud in front of that star, all right, and I observe it with my expensive telescope, when that light passes through the cloud, it gets absorbed, gets reduced somewhat, and you get information about the star and any interactions that light had with the object itself. Sure. No, it's okay. Okay. So then what you get is the stellar spectrum, okay, and then these very narrow absorption lines here, some of the other ones, that are actually from the object itself. So they're atoms or molecules sitting in their ground state, very cold object. There's no energy around, right? So the energy gets shared by collisions, but if you're at 10K, it's pretty cold, right? So things like to hang out on the couch and eat popcorn and watch TV. And then the starlight comes along and they'll absorb that light preferentially, and we can observe it with our telescopes. Okay, so you can then go out and, you have the emission, same with the absorption. It's proportional to the amount of molecule or atom that is there. Okay? So we can look at this, these objects. So here, this is carbon, nitrogen, oxygen, magnesium, silicon, and iron. 0 here is where its abundance is the same as in the sun. All right? So we can look at it. Nitrogen has about the same abundance as the sun. Oxygen, maybe a little bit less, but the errors are large. Carbon is probably less, but again, errors are large. But the HW refers to the hot cloud, the warm cloud, and the cold cloud. Let's just focus on the cold cloud. As you get to the heavier elements, the true metals. So in astronomy, anything greater than helium is often considered a metal. Not to me. The metals are these guys over here. And you can see they are substantially what we call depleted. That is, the elements are missing from the gas. So I was talking about the solid state. Now we're observing an interaction from the cloud with the gas in that object. And the abundance of iron in that object is not in the gas. So where is it? Well, it's likely in the dust. That is, it's telling you that the silicates, the magnesium, and the iron is not in the gas, and it's likely comprising those dust grains that you're observing in that montage of B68 that I showed you that are absorbing the starlight. Another way of looking at this is that, again, this is the depletion relative to the sun versus what's called the 50% condensation temperature, when half of the mass would condense into the solid state. And this shows this very nice correlation that when you get to these high condensation temperatures, that is, it's easier for the element to condense and go into the solid state, there's less of it around. So what does this mean, of course, is that we now know, this is an example of an object where these dust grains are being formed. We have found the seeds of the Earth, right, via observation. We now know where the Earth came from, and it came from these tiny little particles, again, that had a gigantic party, really big party, and made the Earth. All right, so now let's talk a little bit about the gas. So I'm going to talk about the global properties, some of the internal properties, and large scales, and also get to following the carbon, hydrogen, and nitrogen. So this is a beautiful picture obtained by Barnard in 1907. You know, Barnard was one of the first people to put a camera behind a telescope, and he sort of categorized the heaven. He wasn't one of the first ones to do things, but these are these dark regions in space, right? Okay, and what of course we now know is that these dark regions of space are not dark. They are filled with material. They are filled with, well, clearly the dust that we just talked about that's absorbing the starlight, but also gas. And by mass, there's 100 times more mass in the gas than the dust. So that's observation determined. So just to show you that this is not a negative image, this is an image of CO obtained towards that same region. So let's go back and forth. So you can tell that, you know, where you had that dark lanes, in particular this thing right here, there we have the CO emitting and following that very nicely. Okay, and so this was put together by myself and Mario Tafalia, again showing that picture and the correspondence, but now I'm just going to zoom in on this area right here. And instead, now this is observing with an isotope of CO. This I think is C18O. So we can see there's all this structure here. Okay, there's peaks. So what we're doing is we're taking our telescope, our radio telescope, and observing at this point, getting a spectrum, going here, getting another spectrum, going here, going here, going here, and mapping the emission. All right. So these are presumably mass condensations, or if you will, fragmentation of this general object. So here it is again, all right? Same object, but now zoom in. This is the DSS. the sky survey. And so here you have these dark spots. All right, now I'm going to observe it instead of using CO, that's what that is, I'm going to observe it with N2H+. This is a molecule that we now know traces dense regions chemically, but it also is a high dipole moment molecule. And I told you it only traces denser regions. So here you have this more extended material. Now I'm picking out only dense knots within this same region. All right. Here's another molecule, sulfur monoxide. And this is the continuum emission from dust grains. So this is the dust grains emitting that starlight again. And you see these dense condensations. So this is the regions that are collapsing or will be collapsing and making stars. So that's the march, if you will, towards greater density. Now, we can survey and have surveys starting first with the IRAS satellite, and then with ground-based near-infrared studies, and then Spitzer, and then WISE, and CARI, and a whole bunch of things. We can actually look and find out where the distribution of young stars are, and surprise, surprise, this is how we know that molecular clouds are the sites of star formation. So this is, again, that map of the Taurus molecular cloud with the young stars superposed on it, and you can see that the stars follow, by and large, the distribution of the gas, although not always. Right? All right. So the original way that the sort of densest regions where stars were going to be born were found was these dark regions on the Palomar Sky Survey plates. So these things right here. So we knew that they were about a few arc-minute size, and they were common in the nearby clouds. So the closest clouds to us, Taurus, Ophiuchus, so on. All right, and they were in the vicinity of IRAS sources. And again, IRAS sources are objects that we thought were young stars. Okay. And now today, we can observe them with our telescopes in a whole host of molecules and map out. So each of these would be one of those little dark objects, and you can see this central concentration and emission, sometimes associated with the star directly, sometimes indirectly. All right? And I'll show you all the great things that we can do with this. We can study the physics and we can study the chemistry, all using these different molecular lines. All right, so there's other things. There are, you know, the nearby clouds, but then there are objects that appear to be completely isolated that don't have any cloud around them. So Taurus is a gigantic molecular cloud, and we see dense condensations within it. And then there are these objects called Bok globules, which are also optically defined, but they're very isolated, and they come in a whole bunch of different sizes. And this is just one, the B68. And this is just showing you it on the star field. So there's, you know, a chain of these things. This is the snake. You can figure out how it got that name. So the idea is that maybe there was a lower density cloud. These are all dense condensations. Supernova perhaps came and blew away the cloud. We don't know. But they're clearly dense objects. Okay. So what we do is we study these things using all the tools at our disposal, the emission from the dust itself, the emission from the molecules, and we determine that their typical diameters are on the order of about 1/10 of parsec. So here. This is emission from ammonia. Masses on the order of several solar masses. Typical temperature is 10 K. All right, if I have a size and a mass, I can get a mean density. It's on the order of about 10 to the 4th or so. Okay, and so these are the regions that are going to be making sun-like stars. Now, I talked about how you get mass. How do we get temperature? There's several different ways we can approach it, and this is the simplest. One is if you have optically thick emission. So carbon monoxide is typically optically thick. But if it's optically thick, it actually tells you something about it, temperature. So how does that work? Well, in radio astronomy, what we do is, you know, here's your emission, all right? So this is the black body, but now we're on the Rayleigh-Jeans side, the long wavelength tail of the black body spectrum. And so you have a temperature here, and this is the intensity that you observe. In radio astronomy, we're at the wavelengths that correspond to the Rayleigh-Jean scale. So we work in temperature units. So you can look at it this way. So we have your observed intensity is your black body at some temperature it's emitting, and you try to subtract out whatever the background is. And then it goes as 1 minus e to the minus tau. All right, that's for emission. Now I'm going to convert this to temperature units, so I just get rid of all of these other quantities. And I get some temperature of the object, the temperature of the background, and the optical depth. Now, so this is what I observe right here, this delta T. Okay? Now, if it's optically thick, this goes away. All right? The background temperature is the cosmic microwave background. That's about 3 degrees Kelvin. I know what that is. All right? So that means my delta T is basically equal to the temperature of that object. And so that is a direct way to measure the temperature of material. So we can get the mass, we can get the temperature, we can probe fundamental properties. The other thing we can do, and I'll show you this, is that we can actually get kinematics. And this is also kind of neat. And what we find is that the cores are dominated by subsonic motions, and it's best shown on this. So why is this a big deal? Well, the interstellar medium is a very violent place. And things are being pushed around all the time with basically turbulence that actually is supersonic. But the areas where stars are being born, actually that turbulence is dissipated, and the objects we're finding are generally thermally dominated, certainly for the low mass star formation regime. So here is an example of an object. So here's what we're doing is you take a spectrum and you measure the width of the emission. Okay, the full width half maximum. So what you have here is you have an emission line of a molecule. All right, one molecule is coming out. It's at one velocity, and it can do the Doppler effect if it's heading towards you. Right, the emission will be blue shifted. If it's heading away from you, it's red shifted. But you have an ensemble of molecules. They're all moving at different velocities. So that spreads out the line in velocity space. And here you go, you have different widths, although it's very hard to discern in this plot. They actually are different. And if you look at this object, what you see is that there's a minimum where it's densest, and then it gets higher when you get outside of it. The other thing you can do is you can determine rotation. All right, so to make a disk, you have to have an object that's rotating and has some angular momentum that allows for the collapse to go down through the disk. So you'd think that these objects would be rotating, and maybe they're rotating at different rates. So here is that Barnard 68 object now observed in an isotope of CO. All right, and I can look at, for each spectrum, I can determine the centroid of a velocity. Where is most of the emission? And you see that there actually is this smooth gradient across the object. What the object is doing is it's rotating very slowly. So we can measure rotation. We can do that just via emission lines, and you can do that in disks. I'll show you that. And this is important for star formation. Again, this is a little bit going off topic, but I think this is really neat to show. Molecular clouds are huge. So this is the specific angular momentum. All right, molecular clouds are up here. Stars are down here. So you somehow have to take this angular momentum and get by 1, 2, 3, 4, 5, about 6, 5 orders of magnitude. You have to dissipate that angular momentum to make your star. That's the angular momentum problem in star formation. And that's a very, very fundamental aspect. And we can get at it by observing emission lines in the cloud. We can observe them in the cores. We can observe them in the protostars after the star has been born. So you can see we're losing angular momentum here. And then there's binaries. And then, of course, single stars. You can observe rotation in stars themselves from the lines. Okay. Now, how long does these various phases last? So what I've been talking about for the most part here is the molecular cloud and the initial condensation and most of the objects that I've shown you are before the star is born. All right? So this is what's the so-called pre-stellar stage. And what we'll learn, this actually is an important stage because it's probably where the water that is right here was made. All right, and I think we can show that now. All right, so what we do to try and get at lifetimes is we determine the ratio of cores that have stars and those that don't have stars, and we estimate the lifetime of the ones that have stars using basically pre-main sequence tracks on the Hertzsprung-Russell diagram. That's an astronomy term. But okay, so the starless core to the cores with stars, the ratio is on the order of unity to 3, and that works out to a lifetime that's on the order of about 1 million years, maybe 500,000 years. Time is a real hard thing to get at in astronomy. All right, we can actually study the structures of these objects, and we try to do that with dust, and there's a bunch of different ways we can do it. So one example is when I showed you that absorption of starlight towards B68. All these background stars, they have to pass through, that light from that star has to pass through that object on the way to our telescope. That carries information on the amount of dust that's absorbing that starlight. So if you look at that, towards the center there's a peak of absorption, and then as you go further away there's less and less and less and less absorption. What does that tell you? That this object is centrally concentrated in density. There's more absorption towards the center than there is towards the edge. Okay, so we can actually map out the density structure of these objects. Another way you can do it is from the emission. So that's the absorption of starlight. There's a moth. The peak of the emission also corresponds to a density peak. So here you have, again, another object where the emission is falling off. So the emission from the dust also is proportional to the amount of material that's present. And this is another way of doing absorption, but now you're doing it not with starlight, but with a general background in the mid-infrared. Now, this is, how do I say this? The way you would want to do astronomy, all right, is if you looked at an object, and I would want to observe it every possible wavelength that I could, bar none. Why don't we do that? Well, because we have this wonderful atmosphere that's life fostering and all that other stuff. It interferes with many wavelengths. So, for example, the far infrared is not something we can access from the ground. In some areas of the mid-infrared, you have to go to space to get reliable measurements. So we can't always do that, but now we have telescopes. So here, this is the same object, B68. Now I'm looking at it in the optical from the ground. This is Spitzer at 4 microns, Spitzer at 8 microns, WISE at 12 microns. All right. This is Spitzer at 24 microns. Now I have Herschel Pax at 100 microns, Herschel Pax at 160 microns, Herschel Spire 250 microns, Herschel Spire 350 microns, Spire 500 microns, ground-based 870 microns, and ground-based 1200 microns. And you can actually see some really interesting things going on in this object, right? So it's all dark here, it's all emission here. There are asymmetries. Okay, what's that? That's heat. That means the object is getting heated by this in this direction. And when you get to the really long wavelengths, it's very strongly centrally peaked. That's tracing the density. So in here, you're sort of tracing temperature, if you will, and in here, you're tracing mass.
Can I ask a question?
Please, please, please.
What is the explanation for the temperature for the far infrared, past 100 microns, for instance, to be so weird?
So asymmetrical?
Is there something?
There has to be something there. Yeah, there's an asymmetry in the background radiation field. Has to be the case. Yep. Yeah, please ask questions anytime. All right, so I know this lecture is heavy on physics, but you know that's
So
it's
what provokes
astrophysics.
the real opacity is dust or gas?
Dust.
Gas, no? Dust.
Dust.
Oh.
So in stars it's gas, but in interstellar space the main source of opacity is dust.
I mean opacity in the visible.
Dust. Dust. Right? Because there's if you know the main gas is H2, and H2 doesn't respond to visible radiation.
Yeah.
Right?
Yeah.
Right? So it's dust. Okay, so in that paper they had all that information, and what they determined was this is the temperature of the dust grains. Okay, this is the center, that's the edge. So it's about 18 K at the edge. Heat it. There must be some asymmetry clearly, and then it cools down to about 8 K in the center. The volume density correspondingly is lower at the edge. That's what's right here, and rises to the center. So central condensation means it's on its way to making a star. All right, so gravity is winning in this object, and you're on your path to making a star. Okay, now we want to follow the chemistry and understand something about where the molecules or the elements of life came from. All right, so we can do that too if we know the density distribution of this object. All right, I can then actually extract chemical abundances very reliably. And so here is the mass distribution. This is when you observe CO, isotope of C18O. So here's the center of the object, and it is a minimum in the emission of CO. All right, this is CS, same deal, the peak is here, right here. N2H plus is this other molecule that somehow is different. It is tracing the center. So what you have here, the red line is tracing the mass distribution as probed by the dust. Here's the CO. It's not emitting as much from the center, same for CS, but these other molecules, the nitrogen-bearing ones, appear to emit from the center. So what's going on there is you're having ice formation. As you get denser, the molecules have a greater probability of interacting with the dust grain. All right? And that, you know, if you're going to do astronomy, one thing you need to know is N sigma V. Right? That's the collisional frequency, right? So you have the grains here, the number density of grains, the surface area of grains, and the velocity of the gas. All right? So what that says is, what's going on is, as you get denser, this is getting bigger. Right? You're collecting more grains, and your collisional frequency is getting high enough that the molecules are seeing a grain, and they're sticking and they're staying on. But there's this disparity with the nitrogen. This is, so that was one object. This is B68, which is my favorite object. And so here again we have our optical image. All right, here's the central peak in mass. If I look at CO, I have this partial ring. And now we know that the heat's coming this way. So that kind of explains why, I mean, I had no idea when I got this data why it looked like that. Why isn't it, you know, completely circular? But now I guess we know. And actually I didn't realize that until this very moment. So thanks for that. N2H plus is all emitting from the interior, where CO is not. And then you have other molecules. There's one with an isotope of hydrogen. There's an isotope of carbon. So what's going on again? This is a plot that shows you the general thing. So this is density, okay? This is the time scale in years. This is the time scale to collide and freeze out onto a dust grain, all right? Now, other things are on here. Let's just focus in on one. This is the free fall time. So that's if the mass is big enough that gravity is winning. All right? Now, these central densities objects are on the order of 10 to the fifth. So you can see that the chemical time is less than the dynamic time. That says that this object may be collapsing, but the molecules are going to disappear. Now, this was always thought to be a bit of a bummer, right? Because you want to study star formation. And how do you study star formation? Well, you use the emission from the dust. We talked about that. Use the emission from the gas. The gas has velocity information. Star formation means that you're collecting material. It's moving. The gas can trace that movement, but if a molecule is not in the gas, it's not going to trace that movement. So that was unfortunate if that's the case. But we have this one molecule. If I go backwards, this guy right here, that's doing something different. Okay? So that's a molecule that chemically, for some reason, is tracing the center of the object. So what's going on there is that's just chemistry. So that one molecule, N2H plus, okay, that is formed from N2, our favorite molecule in our atmosphere. All right. Its main destroyer happens to be this one molecule that's very abundant, CO. So this reaction happens in space, and it makes this molecule plus something else, right? But if the CO goes away, then its main destroyer goes away, and its abundance goes up. So that's why it's doing something a little bit different. And this will prove to be very useful when we want to get into disks and study planet formation, as we will learn. Okay. So what happens, of course, is that when you have this question of freeze out, where the molecule's freezing onto the surface, the grain has to be cold enough for the molecule to condense. All right. So if the grain temperature is greater than the freeze out temperature, if you will, so CO freezes out at 20 K. If the grain temperature is 30 K, the CO would evaporate. All right. If the grain temperature is less than that, the CO will freeze onto the grain. If I go back to here, this is the evaporation timescale for CO. All right, at basically for each density here. And this is at the temperature of the object, which is 10 K. So you can see as you get to dense enough, it's just going to freeze onto the grains. It has to warm up. The star has to be born before you're going to bring things off. Okay, so let me just spend a few seconds. I'm not going to do too much on the chemistry, but I think it's important to understand how the molecules form if we want to understand how you're going to track the molecules. So what we know, in this case, I'm going to use water as my foil because every step in the sequence has been measured in the lab. So there's a source of ionization in the clouds, and it's basically cosmic rays. They're energetic protons or atomic nuclei that are thrown out by a supernova, or maybe X-rays. They come along, they ionize H2, that's the main gas. That makes eventually this molecule H3+. This is the engine of growth for molecular complexity in the gas. That'll react with your atom oxygen, make OH+, that reacts with H2. If it's going to react with H2 is most abundant, so if it reacts with H2, it just happens. It goes right down here to H3O+. That particular molecule doesn't react with H2. It waits around to find an electron and make sure water, OH, and O. So this process can happen in the prestellar core or the protostellar core. Before the star is born, it can happen after the star is born, and it can also happen in the outer parts of the protoplanetary disk. All right. However, it's actually fairly inefficient. It only takes about 1% of the cosmic oxygen and sticks it in water. Another way you can make molecules is if you have your atoms running around, and the atoms, instead of the molecules freezing out on the grain, the atoms freeze out onto the grain. So now you have the atoms sticking on the grain surface. And they actually are mobile. They don't sit in place, especially the light hydrogen atoms. And they zoom around, and in timescales of months, they'll find each other, and they can react by catalytic chemistry, and you can make molecules like water. You presumably can hydrogenate carbon, make methane, you can make ammonia by this way. And this is very, very efficient. And in fact, this is the way molecular hydrogen is made in space. There are no known gas phase pathways to make the most abundant molecule in molecular clouds. It has to be made on grains. And that has now been proven in laboratory work as well. Okay, now, one other aside here, and that's isotopic fractionation. This actually is very, very important if you want to track where the Earth got its water. And what do I mean by that? That is, if you look at the main isotope of hydrogen is deuterium. Deuterium was created in the Big Bang. Okay, the abundance of deuterium is about 10 to the minus 5 relative to hydrogen. How do we know that? Because we measured it using absorption lines of hydrogen and deuterium, using, I think this was mostly with fuse, maybe with HST as well. So this is a bunch of different sight lines with different column densities of hydrogen in them, and there's the D to H ratio. So it's about 10 to the minus 5. See, it's times 10 to the 5th.
This is in the ISM.
This is in the interstellar medium, yeah. And there's actually, you can see it's very tightly confined here, and then it gets a little bit, what the heck's that? Well, there's something, the sun exists in a gigantic bubble. It's called a local bubble. It's the border of the local bubble. Okay, so the main isotope of hydrogen is deuterium. We also talked about the other isotopes. Now, you can fractionate. The chemistry can favor the transfer of the heavier isotope. In the case of hydrogen, it's deuterium. Hydrogen has a proton. Deuterium is a proton neutron. Right? And there's a difference in the 0 point energy. What is that? Is that the vibrational 0 point energy of the deuterium is lower than that of the hydrogen. Okay? So there's an energy difference between the two. So H2 and HD, when you make HD, have slightly different 0 point energies. Okay? And so the enrichment, that is the transfer, the chemistry will favor the transfer of the deuterium, and it'll depend upon delta E, the change in the 0 point energy, and the temperature. And the change in the 0 point energy for HD and H2 is only about a couple hundred K. All right, and the biggest difference amongst the biogenic elements, hydrogen, deuterium, carbon, oxygen, is in hydrogen. So it's got 1 atomic mass unit versus 2, whereas you see that the carbon is 12 versus 13. So what does that work out to? What that means is that at low temperatures, the chemistry favors the transfer of the deuterium as opposed to the hydrogen. What do I mean by that? That if a molecule is reacting, say I take my H3+, that's the engine of growth in the gas. So H3+, okay? And that can react with HD, and that can make the deuterated form of that molecule plus molecular hydrogen, okay? Now this reaction can go in both directions, all right? But this one, this direction here, needs a little bit of energy to get over it because of this right here.
Is it in gas phase?
This is in the gas phase, okay? So when you're in the gas phase, you get the cosmic rays, they ionize this, and if you're less than about 50 K, the reaction goes in this direction. If you're greater than 50 K, the reaction goes in this direction, okay? And it stops the process. So what happens? What happens is that, I told you that water in the gas phase can form by this molecule. The deuterated form can form through this molecule. Okay? So you can get HDO over H2O that will be greater than the 10 to the minus 5. You can take deuterium that was in HD and stick it in other molecules and enrich them. All right? Now this process also happens on the grain as well. It's powered in the gas. Okay, it all comes from this reaction in the gas. But it also gets transferred onto the grain. So you get large deuterium enrichments on the grain as well. Now why do we care about this? Is this just an aside? No, it's not, because the Earth's oceans have an enrichment of deuterium. The temperature in the gas at which the Earth, out of which, where the Earth was at 1 AU, was hundreds of Kelvin. This reaction would not have happened. It cannot happen. All right? So that tells you right away that the Earth got its water from some source where that water formed. That source was really, really cold. At most, it was 10, 20, 30 degrees above absolute zero. There's only two places that could happen. That's before the star is born, or way in the outer parts of the protoplanetary disk. All right. In my last lecture, I will prove to you that that can't happen. And our water came from 1 million years before the star was born in some area that was very, very cold. Okay. We know this happens because we observe it. All right. In regions that are cold, 10 degrees Kelvin, we see the ratio should be 10 to the minus 5 between the deuterated and the main. If this process is not happening, and typically, for a whole bunch of different molecules, there's formaldehyde, HDCO, ammonia, ammonia is 0.005 instead of 10 to the minus 5, formaldehyde 0.01. And this is an object where this is the D-to-H ratio in N2H+, and it's, as you get deeper into the object where the object's getting colder, the ratio is increasing. All right, so the chemistry actually is happening. So this is the engine to give you this sort of isotopic fingerprint that we're going to use to try and trace back the origin of our water. And you might also actually try to trace back the origin of the organics as well. All right, so from looking at all the chemistry and learning what we know, before the star is born, we have this sort of structure that actually molecules, the neutral molecules, are mostly tracing the outermost edges. So this is what's called visual extinction. This is the depth into the object. So this is the surface exposed to starlight. This is the dense region where the star eventually will be born. 10 minutes here? 10 minutes before questions? Yeah? Okay. And so we have the undepleted stuff. Then we have molecules that trace, the nitrogen things. And if everything freezes out, you can still have this molecule here, H2D+, that has a dipole. And we can use that to trace the center of regions. Okay. We also can observe molecular ices. So here's observations. So ices, they can't rotate, but they can vibrate. And if you put a strong background source between you and it, you can observe those vibrational modes. So here's actually the silicate, the core itself. There's water, absorption line of water. There's CO2, CO, and so on and so forth. And based upon these observations, we actually know that the abundance of water has to be made by a solid state chemistry. That is, the chemistry on the grains itself, not in the gas. Okay, so the prestellar phase goes like this. We make simple molecules. We make simple ice mantles dominated by water ice. And that's formed via catalytic chemistry. The CO actually is made in the gas and is frozen. Now, a half of the carbon is in the gas and CO, and half of it is in that refractory. So when I talked very briefly, I told you that interstellar dust models, there's silicate grains doing absorption. There's also carbonaceous grains. And based upon observations of elemental depletion towards diffuse regions, we know that half of the carbon is in refractory dust. This will become important when I try to make the Earth. All right. Most of the O that's not in CO is found as ice, and we have large deuterium enrichments. Okay, now we make a star. A star is formed. All right. Now we actually trace them, a lot of things through star formation, because you have all this energy coming out, and you can trace them from the dust. All right. You also have an outflow now. You have shock gas in the outflow. So there's lots of energy going on. Lots of energy into the system. You can observe a whole host of different lines. And one of the things that this phase is characterized with is it has a warm envelope, basically a heated envelope of gas, where the ices have boiled off. And the richness of the chemistry that's occurring in the solid state, which appears to exceed that of created in the gas, is revealed. When you're at 10K, anything that's happened on the ice, you can't see things. You can see the most abundant ices, water. Lesser abundant ices we can't see via that absorption observations. So you hot core, all of a sudden this rich complexity is revealed. All right, so this is an example of a protostar seen in the dust. So this is where the star should be. There's no star emission. Okay? It's all absorbed and re-emitted in the far infrared. And then there are objects where you can sort of start to see the star. And there's still some excess emission. The star should be falling off here, but it's not. And so we classify these things as class 0. They have the biggest envelope. Class 1 have less envelope. And class 2 are just the star and the disk. So astronomically, there's a classification system that if you get into this business, you'll hear about it. So here's a pretty picture from the Herschel Space Telescope. So these objects, protostars, are emitting in the far infrared mostly. All right, so here's a far infrared 70, 160, 250 micron map. And this is looking just at 70 micron. You see all these little point sources. These are young stars that were born in the past 100,000 years. Another example. This is an object where we're looking at it here in the mid-infrared. You see absorption. All right, and then you see all these little dots here. These central, they're young protostars again that have been born very recently. Okay, we can look at these things with spectroscopy. This is one object in NGC 1333, and this is infrared from 220 to 200 microns. Look at all those emission lines. That's mostly water. So the red, the blue is water, red is CO. We also see OH. And I'm going to end with this last one here. So this is one of my favorite constellations. Maybe you know it. All right, I'm going to zoom in right here. Right here. This is the Orion Nebula. This is another very pretty photograph from ESO. So here is a cluster of stars that's being born, a trapezium. There's all this diffuse stuff. That's the dust that's reflecting starlight towards us. This object actually is sort of, the trapezium is sculpted. There's a cloud behind it, and it's sculpted out, and it kind of, there's a lip here. That's what this is. It's called the bar. Now, if I were to look at this in a molecule such as C18O, it would look like this. So there's this, here's the bar, you really see it right here. All right? There's a condensation here and another condensation there. So that's where stars are being born, in this case massive stars. If you point your telescope right towards that object, you see the ices, the organics, and water being revealed. So what is that? So here are, again, if you could do astronomy the way we want to do astronomy, not only would I take pictures at every wavelength, I would get a spectrum at every wavelength. And with the Herschel Space Observatory, we were able to obtain the biggest and most complete spectrum of star-forming gas that we've ever been able to obtain. So this is from about 460 gigahertz to, that's about 409, it's about 450 microns or something like that, all the way up to 1.9 terahertz, which is about 150, 160 microns. This is towards Orion, that's that region there. This is towards the galactic center. This is another region in Orion, and this is a a region that doesn't have a star, but it's exposed to ultraviolet radiation. Now, what is this? This is noise here, and that sort of noise. But all that stuff there, that's emission lines. That's molecules saying, hi, I'm here, identify me, if you can. All right, so there I'm smoothing it. That's CO, rotational emissions, going up. This is a satellite, so we actually can observe water. There's water lines. And now let's zoom in a little bit. So these are different star-forming regions. So look at this. Isn't that beautiful? I mean, for a spectroscopist like me, I just looked at it and said, wow, that's methanol. That's methanol saying, here I am. This is the galactic center. This thing is much more distant than that. So this looks weaker, but intrinsically, it's orders of magnitude. It's like a beacon. There's an ethanol in this object saying, come here and drink. And there's, you see, it's weak here. This is actually at the same distance as that, so there's less methanol here than there is there. And this is exposed gas, no star, no evaporated ices, no methanol.
What is the absorption?
The absorption is CH. So this spectrum has, well, we now know it has about 40,000 lines. They overlap, 1 million independent spectral channels. And the way we analyzed this was I had a graduate student, and I killed him. But no, actually, we got 15 people to work together to analyze this spectrum, just this one spectrum of Orion. Another 15 to do one of the other spectrum, and it was managed by the graduate student who I didn't kill. He did an awesome job. So in this region, these are the molecules that we observe. I don't expect you to know many of them. One of them is water. You know that one. This is methanol, ethyl cyanide. There's formaldehyde there. There's a whole bunch of things. So lots of molecules. When I tell you we detected a molecule, I'm not lying. This is what methyl formate with over 1,000 transitions. So the white is the data, the red is our spectral model, and we derive how much of the molecule's there, what temperature it is, and when I say again we detected it, I mean we know it's there with very good accuracy because we have thousands of transitions. So this is our fit to that spectrum, telling us all the different molecules that are there. We can measure their abundances, and we can ask how much of a given species is there, and what's happening to the carbon, what's happening to the oxygen, what's happening to the nitrogen. And we're fitting the entire spectrum at once, so I'm zooming into lower levels, and you can see even though we weren't fitting down here, at these levels we actually were by fitting all at once. And there's other frequencies as well. I don't need to get into it, but this is at the higher frequencies. There's less lines. This is SO2, I think. All right, it's a particularly triangle. That's a weird astronomical line. Okay, the other thing is, and I'll end right here, these regions show enhanced levels. We know that they're organic rich, so the chemistry of star birth creates the beginnings of organics. That's one point. All those emission lines telling you that the chemistry of star birth is making those organics. Now the other thing we know is that they have enhanced levels of deuterium fractionation in both organics and in the water. All right? Now, the temperature of these regions we can measure. We have 1,000 lines. We can measure the temperature. It's greater than 100 Kelvin. This chemistry does not happen. In fact, the opposite is happening. You're destroying the deuterium enrichments. So if you see deuterium fractionation, it has to be an ice that was evaporated. It's a fossil. It's a relic of an earlier phase where it was colder before the star is born. So we know that the beginnings of organic chemistry also started before the star is born, maybe assisted a little bit as the gas warmed up and more things might happen. Okay, and so I guess maybe I'll just end here. So what we see, actually, these are formed by a catalytic chemistry on the surfaces. We see the precursors to the simplest amino acid. We see sugars. We see contributors to prebiotic synthesis. Cyanoacetylene is one molecule that if you stick in the lab with a couple other molecules, you can make RNA. And we see HCN dimers, and one of the DNA bases is 5 HCNs. So if you could take 3 more HCNs, you can make a DNA base. All kinds of things. So the beginnings of organic synthesis is seen in interstellar space. And so tomorrow I'll pick up and talk about what happens in the disk and what happens from what we know in the solar system, and then try to put all this together and tie a bow around it on how you can make a world that has all these things incorporated in it. And again, as I will show you, we don't know all the answers yet, which is actually a really good thing for you. All right, thanks.